Welcome back. The video we're going to be looking at today is our first in trigonometry, and it's on radian measure. Now, some of you may have used radians already, and if you have, that is fantastic. I'm going to assume that we're pretty much starting from scratch on this one, though, for those that are not familiar with radians, and we'll cater to them. And hopefully by the end of the lesson, you'll be at least semi-comfortable. I will say that I know all students are skeptical about using radians at first as a unit of angular measurement, but you can become much more proficient in it as you keep using them. So let's jump over to our lesson and see what we've got to do today. First thing I think we should do is definitely look at what even is a radian. Why are they important, and well, why do we bother using them? I will say that many of the sciences the physical sciences such as physics do tend to still use degrees. Radians are useful in higher level mathematics when you want well, we say they're measured in radians, but really it's just a radian is the system. The actual measurement itself is unitless. So when we say something is 2 radians, it's actually just 2, as opposed to like 5 degrees. The reason that we want a unitless measurement for angles is so that we can use a variable that represents both an angle and a not angle in the same equation. So something like y equals x sine x. If x is in degrees, then you have degrees times unitless, which you may not want. Or you could have unitless times something that doesn't work because normally sine only works with degrees. Unless, of course, you have a unit like radians. Okay, anyway, jumping into our picture here, to explain what 1 radian is, I'm just going to draw over top of the left diagram here. I realize they're already highlighted, but I'll highlight them again as we go. So here's a unit circle, and that red part that I just highlighted is 1 radius. And for our purposes, let's just say that this is a unit circle, so we'll just say radius equals 1 unit. We can say 1 centimeter. If the angle of measurement is 1 radian, what that'll give is an arc length out here that's also equal to 1 centimeter. So it's basically saying that the number of radians is equal to the distance of the arc, or the length of the arc, which makes it kind of useful. So now in this, if we do a full circle, which by the way, I'm just going to write up here, a full circle is 2 pi radians. So that means that 2 pi radians goes all the way around once. And even though the unitless, I will write rad for now just to help make sure that you understand when I'm talking about an angle and when I'm talking about something else. It means that if it's 2 pi radian angle, the distance, or the circumference, will be the full circumference of a unit circle, which is 2 pi centimeters. So if you're working with arc lengths, radians can be very useful because your distance of your length of an arc is exactly equal to your radian measurement times the radius. If you had not a unit circle, but a circle of radius 5, then you would have 5 times 2 pi centimeters to go all the way around. Okay, over here, I've just put a circle with a whole bunch of circle terminology on there, just for kind of a general reference. Most of these you already know, so hopefully you know tangent, because we should have talked about that already. That's just a line that glances off the curve. You definitely should know circumference. The center of a circle is pretty obvious. Radius is pretty obvious. Diameter is pretty obvious. Arc, I'm going to put a big check mark there because that's what we just talked about. That's basically the distance around the circle. So if you think of like a circular track, that's the part you're running. And then the other terms like chord, segment, and sector, we're not going to use as much, but they're there for your reference. And in case we come back to them, we'll talk more about them then. A couple other pieces of terminology. Again, not that they come up a huge amount, but enough that you should know what they are central angle and subtend. So central angle is just the angle between 2 radii. So just to kind of draw this over here, if I just take any 2 lines coming from the center, we'll pretend that's the center. My drawing's not great. This would be the central angle. Now a subtend is the arc opposite a central angle. So it would be this arc here. Those could come in handy. Again, I don't use the word subtend a lot. I just refer to the angle in the middle because most people know what that means. And the arc is usually pretty obvious based on what angle in the middle we're looking at in a picture, diagram, question, whatever. Okay, so I already mentioned that a full circle is 2 pi radians, and that's actually going to give us our definition of what is a radian relative to a degree. And the answer really is just 2 pi radians is a full circle, so that must be equal to 360 degrees. Now, more commonly, we're going to just use that pi radians is 180 degrees, just because it's a little bit more easy to work with. And again, when it comes down to it, people make this sound like it's a huge difference. Really, this is no different than measuring in centimeters versus inches or measuring weights in kilograms versus pounds. It is really just a unit conversion. Degrees, I was going to say, actually, the radians being the unit preferred by high-level mathematicians, degrees being preferred by pretty much everybody else. I will point out that my background is applied mathematics, was essentially physics. I worked with degrees all the way through. So it's not that degrees are wrong by any means. It's just there are a few high-level branches of mathematics where radians come in handy. And so we thought we should introduce them to you in high school. Anyway, let's convert a few measurements here. We've got a couple of angles, and we're going to convert them into radians expressed as a decimal number. So here's all there is to it. I know this is going to sound funny, but whenever you're doing unit conversion, if no one's told you this before, you can get it easily. Because some people are like, do I multiply? Do I divide? What do I do? The answer is multiply by a fraction that's equal to 1. Because multiplying any number by a fraction equal to 1 keeps it equal to itself. It's just how we make that 1 look that is helpful. So for instance, I want this fraction to be equal to 1, which will be true as long as the top and bottom are equal to each other. So I'm going to put 180 degrees on the bottom and 1 rad on the top. Pi rads on the top. Because we just saw up here that pi radians at 180 degrees are equal to each other, which means that this fraction is actually equal to 1. Okay, why is that useful? The answer is we can cancel a few things out. 90 degrees over 180 degrees is the same thing as 1 over 2. 1 times pi rad over 2 is just pi over 2 radians. That by far, to me, is the easiest way to do a unit conversion. Multiply by a fraction equal to 1, where the top and bottoms are equal but in different units. 1, the unit you want to get away from, you put that on the bottom, and 1, the unit that you want to go to, which is the one you put on the top. Now, one more step here. I probably should have done 1 and 2 backwards, but we'll see what happens. This one says to express them as decimal numbers. Now, just because it's radians doesn't change the fact that pi is pi. So all you have to do is punch that into your calculator, 3.14 divided by 2, and you get 1.57 radians. Now, I will point out that just for simplicity, I will always use 3.14 in my calculator for the numbers I give. Of course, we know that pi keeps going on for a while. So my answers will be technically approximate, but they're accurate down to 3 significant digits, so we're all good. Okay. For the next one, we do 60 degrees. We want to move away from degrees, so we put 180 degrees on the bottom, and we want to get to radians, so we put pi radians on top. We can cancel out there. That's 1 and 3. So that gives us pi over 3 radians. And again, we punch 3.14 at our calculator, divide it by 3, and we get out approximately 1.047 radians. I will point out that these are considered approximate, and the textbook will often refer to approximate versus exact. Approximate usually means decimal. Exact means leaving it with a multiple of pi. All right. This one here, before we even do this one, I just want you to kind of start thinking in radians, which, I realize for most people is a big challenge. It's like trying to learn a new mini language. It takes a little while to get used to until your brain kind of naturally thinks that way. But 350 degrees is almost a whole circle. And a whole circle is 2 pi radians. And 2 pi is like 6.28. So I'm assuming this is going to be about 6 radians. It's pretty close to 6 radians. So when we do this, we're going to do 350 degrees. Put degrees on the bottom, 180 pi radians on the top. This one doesn't cancel out as nicely, so I'm not going to bother trying to do it manually. I'm just going to literally punch this into my calculator. 350 times pi, 3.14, divided by 180 equals, and my answer is 6.106-ish. All right, so we can see that when the angles are kind of pretty, and I think you'll recognize those as being kind of special angles. Special angles being 30 degrees, 60 degrees, 90 degrees, 45 degrees, and so on. That this pi thing works out really nice. The pi over 2 radians, the pi over 3 radians. When the angle's not as pretty, decimal numbers do seem to be a little bit easier. And let's do the last one. 180 degrees on the bottom, pi radians on the top. Again, just punching into my calculator, 10 times 3.14 divide by 180, and I get 0.174-ish. By the way, if you add up these two numbers, you should get 2 pi. Just because 350 degrees plus 10 degrees is a full circle, 360. For the next part, let's convert these using the actual multiple of pi method, which is often a preferred way of expressing radians. Another way to think about this is if you think about 180 degrees as being half of a circle, then pi radians is half a circle. So 90 degrees is a quarter circle. It should just be pi over 2. Because 180 is half a circle. This is a quarter of a circle, so it should be half of pi. Now, I will point out that the actual calculation, should we choose to do it, is exactly up here. We already did it. We had to do this as part of the previous question. 60 degrees. 60 degrees is 1/3 of a half circle being 180 degrees. So that should just be pi over 3. And sure enough, if we look up above, yeah, it was pi over 3. Okay, so for nice angles, converting to radian measure as a multiple of pi is actually pretty straightforward. Now here we still have to do the trick. Now we do it exactly like we did it above. 350 degrees times 180 degrees on the bottom, pi radians on the top. And really all we're going to do is do the 350 divided by the 180 and try to put that as a fraction in lowest terms. So 350 pi over 180 is 35 pi over 18. I don't think we can divide the 35 by anything else that's useful. Factors of 35 are really just 5 and 7. Yep, 18 is not divided by those, so that would be our exact radian measure, 35 pi over 18. Now, if we did this one, This one's actually a little bit easier. 10 degrees times pi radians over 180 degrees. Really, 10 over 180 is just 118, so that's just pi over 18. Which makes sense. If half a circle is pi, or 180 degrees, then this would be 1/18th of half a circle, so 1/18th of pi. So that's really all there is to doing either decimal numbers or multiples of pi. It's the same method, it's just whether you punch it into your calculator, punch in the pi as 3.14, or you leave it as an exact fraction. These are all going to be approximate up here, and these are exact. And exact is usually what we want to work with. But for some applications, much the same way that in any other calculation we do in mathematics, sometimes in real applications, approximate's good enough. So for instance, no one wants to know that it took me, 13 pi minutes to walk to a friend's house. They just want a number. So even if it's exact, sometimes we don't care. Okay, now let's work backwards and convert radians into degrees. We're going to use the same trick we did before with any unit conversion. We start off with pi radians, and we multiply by a fraction equal to 1. And that fraction, again, we're going to use the 180 degrees equals pi radians. This time we want to get away from radians, so we're going to put that on the bottom. And on the top, we're going to do 180 degrees. So this is basically just the exact same fraction upside down as we used before. Because before we wanted to get away from degrees and 2 radians, here we want to get away from radians 2 degrees. These cancel out. We're left with 180 degrees, which hopefully you recognize, since by definition, pi radians is 180 degrees. For this one here, can you guess what pi over 6 radians is going to be in degrees without actually doing the calculation? At least not formally. So this is basically a half circle divided into 6. 180 degrees divided into 6 should be 30 degrees. But if we want to do it more formally, pi over 6 radians times pi radians on the bottom, 180 degrees on the top. The pi's cancel out, as do the radian measure. Usually don't bother canceling out the actual unit, but yeah, it's there. And so this is really just 180 degrees over 6, or 30 degrees. Okay, in my experience, these are the ones that always mess people up because they kind of forget how they work, but they do. This is 1 radian. We put pi radians on the bottom because we want it to go away. We put 180 degrees on top because that's equal to pi radians. And the radian unit itself cancels out. But really what we're left with is 180 degrees over pi, and a lot of people get stuck there on what to do. And I want to remind you that pi, even though it is measuring an angle, technically, pi radians is really just the number 3.14159, etc. So just take 180 degrees in your calculator and divide it by pi. And you should get out 57.3 degrees, I think. I'll be honest, I always just express degrees as whole numbers. Unless you're a sniper or an engineer designing a skyscraper, I don't think we're going to worry too much about being off by part of a degree. It's a very small part of a circle. Okay, and finally, 0.36 radians. We put pi radians on the bottom, 180 degrees on the top. The radian unit cancels out, even though it technically isn't a unit. And now again, we can just punch this into our calculator. 0.36 times 180 divided by pi, or 3.14. And when I do that, I get out an angle of 20.6. I'm going to round that up to 21 degrees. If the textbook asks for an angle in degrees down to 1 or 2 decimal places, I mean, you can do that. It doesn't make any difference. The math's no difference. Just I don't bother putting degrees any more accurately than a full degree. Okay, arc lengths. Just before we get to the actual calculation of an arc length, just going to put a little reminder that the circumference of a circle is 2 pi r. Now that's not radians, that's actually distance. Circumference is measured in centimeters or whatever, but it is going to come in handy. Now to find the arc length, and again I'm just going to draw a picture here, center of a circle. This is the arc length, which is a distance. We're going to call it A. You can use different variables for it, it really doesn't matter, but we'll just use a lowercase a. And rather than try to just tell you an equation and have you memorize it, I want you to think about what it means. The arc length, given some angle in here, theta, is just going to be equal to the circumference of a circle times the fraction of a circle. So for instance, if the arc length is a complete 360 degrees or 2 pi radians, then the arc length will be 2 pi times the radius. If it's less than that, it's going to be some fraction. If theta is 180 degrees or pi radians, it's going to be half a circle, so it'll be half the circumference, and so on. So from there, what we can say is this is going to be equal to 2 pi r times the angle theta, or whatever variable you want to use, but I like using theta as an angle, over 360 degrees. And we can simplify that a little bit, and we can say, I'm going to do it over here, a equals, the 2 and the 360 are both divisible by 2, so I can just say it's pi r over 180 degrees. So that's how to find an arc length of an angle given in degree measurement. I could also say that arc length equals 2 pi r times the fraction of a circle given in radians. And since a whole circle is 2 pi radians, oh, that's where this becomes very nice. The 2 pi cancels out, and we're just left with arc length equals theta r, or r theta. The order of the variables doesn't really matter. I prefer theta r. So if we have an angle given in radians, the arc length is just going to be that angle in radians times the radius, which really goes back to the definition of what radian measurement is. It's when the arc length and the radius are equal, for 1 radian. Okay, given that, let's try to do a few of these. If we have an angle of 40 degrees, what would the arc length be? And the arc length is just going to be the circumference, or the radius here is, we're just going to say 1 unit. So it's going to be pi times 1 over 180 degrees. Sorry, where did my theta go? Oh, my apologies. There should be a pi theta pi r up in that equation. When I canceled out the 2 and the 360, I forgot to put in the theta. Yeah, that would be helpful to have an actual, angle measurement in a calculation involving angles. So I'm going to just start that one over. All right. So arc length equals 40 degrees pi r over 180 degrees. Now the degrees themselves, the unit cancels out. So now all I do is take my calculator and I put in pi 3.14 times 40 times 1 divided by 180, and I get out an arc length of 0.698-ish. And this would be units, whatever that unit is. Usually when it's just generic units, I don't bother writing the unit after, but Yeah, we can do it either way. Same thing here. If we have 135 degrees, it's just 135 degrees times pi times radius, which is 1, over 180. 135 times 3.14 divided by 180 is 2.35, or 2.355. Okay. What if we have it in radians? Well, if we have it in radians, it's actually pretty nice. Our formula just says it's angle times radius. Angle times radius. Perfect. Well, we said the whole idea of an arc length is that the arc is equal to the arc length is equal to the radian degree times radius, of course. And likewise, if we go over here, this equals 1.5 r. So the arc length is just 1.5 units. Okay, so we can definitely see why radian measures are prettier when it comes to doing things with arc lengths. Let's do something similar for a circle with radius of 5. Again, our equation is just the angle times pi times the radius over 180 degrees. And I will point out that just because of the way I do mathematics, I will not include units. I mean, I did do the degrees, I suppose. I did not include the centimeters beside the 5 in the question, but I will state my answer in centimeters. Some teachers prefer that you put units all the way through. I find it really messy. As a physics teacher, it becomes a problem when we're starting to cancel out the same things because there's 5 meters divided by mass, and I cancel out m's, and that screws things up badly. So I leave variables in, but I get rid of units in my individual steps. Anyway, 70 times 3.14 times 5 divide by 180. And this gives me 6.106 centimeters. Same thing over here. And by the way, before I go any further, I'm just going to note that this should be exactly 3 times bigger since it's 210 versus 70. So I'm expecting this to be 18.318, I think. So angle times pi times radius over 180 degrees. 210 times 3.14 times 5 divided by 180. And I get 18.31. It rounds off a little bit different. 317. I said 318. Oh, what a horrible, horrible calculation. Okay, now let's do the same thing if we want to work in radians. Angle's just equal to the measurement times the radius. Now here, because we're giving a distance, no one wants to know that the distance around a circle is 5 pi over 2 centimeters. So we do 5 times 3.14 over 2. It is 7.85 centimeters. And similarly, arc length equals angle times radius, as long as we're measuring in radians. And that should give us 3.5 centimeters. So if nothing else, I think I've justified why arc length, it's much, much prettier to do arc length work whenever you're dealing with any kind of arc length stuff if you're working in radian angles. All right, final thing we're going to look at today is angular velocity, which is a fancy way of saying how fast does something spin around. So we often apply this to things like motors, wheels on cars, hard drives, which is a fairly decent thing to know about if you're buying a new hard drive. So for instance, in example 6 here, I mentioned that the computer spins the hard drive at 7,200 RPM, which is revolutions per minute, or means it spins around 7,200 circles in a minute. and we want to find its angular velocity in either degrees per second or radians per second, or in our case for this example, both. By the way, if you're getting a gaming hard drive, either get a solid state if you can, but if you're getting a physical hard drive, like one with an actual disk in it, most of them are 7200 or 5400. 7200 spins faster, which means it's faster to find files and faster to read files. Just a little tidbit of information there. Okay. Now, I know some people like formulas for things. I prefer not to use formulas at all. I like to logic my way through things and just see what I can figure out without having to memorize formulas. Now, there are some things you definitely want to use formulas for, of course, but for this one, instead of memorizing a formula, I want you to think about this. It spins around 7,200 times per minute. So I'll just put spins per 1 minute. And we want the number of degrees per second. Well, one spin is 360 degrees. And 1 minute is 60 seconds. So this is just straight up logic. There's no formula here. So now we just punch that into our calculator. I mean, we could cancel some stuff out first if we wanted to, which I think is actually slightly easier, but feeling lazy. So 7,200 times 360 divided by 60 equals 43,200 degrees per second. Think about that. That is crazy fast. If I got up to dance right now, I could probably do it at like, I don't know, maybe 80 degrees a second, something like that. I'm not very coordinated. But either way, that's pretty quick. Now, similar, if we want to do this in radians, we actually start off with the same logic, 7,200 spins per minute becomes 7,200. And now instead of saying a full spin is 360 degrees, we say it is 2 pi radians. And just for the heck of it, I'm just going to leave this as pi, as a multiple of pi. 7,200 times 2 divided by 60 is 240 pi radians per second. By the way, I guess I should be consistent here with my seconds. I tend to use SEC for seconds in math and S for seconds in physics. It should be proper. Go away. Okay. So that would be a perfectly valid answer if we wanted an exact. Or we could actually multiply through that 240 times pi and state that that's 753.6 radians per second, approximate. So again, depending on the application, you may want it as a multiple of pi. Sometimes it's a nicer number. Or you may want it as a decimal, which is sometimes nicer, but approximate. Anyway, I think we are going to stop. I think there was a little glitch there, but anyway, we're going to stop there. And there are some homework questions to try. Again, I completely recognize that working in radians for most people takes a little bit of getting used to. So I'm trying to ease you in as best I can, but give it a shot, try them, be honest about it. Even if in your head you've got to kind of convert to degrees first to think about questions. It's much like when you first learn a language. When someone says something to you in another language that you're trying to learn, you don't respond immediately. You convert it to your language in your head, think of an answer in your language, and then try to convert back as you pass your answer along. And I find that to be very similar with degrees and radians. The good news is, as you do that, you will get more fluent at radians until the point where you think in radians, and then the questions become much, much, much quicker. Anyway, I'm going to leave it there. Try the homework questions. Ask me if you've got any problems, and otherwise I will see you in the next lesson. Later.